At 300 kilometers an hour, a train enters a tunnel like a piston in a cylinder. The air ahead has nowhere to go. It compresses, races to the far end, and bursts out as a thunderclap, loud enough to draw complaints 400 meters away. The fastest train on Earth, stopped by a bang. Engineers could build the speed. They couldn't build the silence. The boom only grew worse the faster they went, a hard ceiling on the whole project. So how do you beat a problem that grows with every kilometer of speed? For decades, the answer looked obvious. Make the nose pointed, make it look like a bullet. And in open air, that works. A long nose slips through the sky with little trouble. But a tunnel is not open air. Inside one, the train becomes a piston in a tube. The air ahead can't slide off to the sides anymore. The walls are right there, inches away. So it piles up in front of the nose, in a rising column of pressure. And the nose shape decides the one thing that matters most here: how suddenly that air gets squeezed. A blunt, bullet-shaped front shoves the air all at once. It builds a steep wall of pressure that runs the length of the tunnel at the speed of sound, and detonates out the far end. The shape that made the train look fast was the shape making the boom. And the harder they pushed, the worse that bargain became. Here is what made it a wall and not a speed bump. The boom doesn't rise in step with the speed. By J.R. West's own reckoning, it rises with roughly the cube of it. Push the train 10% faster, and the pressure wave doesn't climb 10%. It climbs by a third or more. In theory, double the speed, and the boom grows around 8-fold. So every kilometer per hour they added brought a punishingly larger bang. There was no brute force way out. A bigger, blunter machine only made a bigger bang. The team ran test trains and watched the numbers climb past anything the neighbors would accept. Those complaints from 400 meters out were already coming in. Eventually, they stopped. They gave up running tests above 350 kilometers an hour, because past that point, the boom was simply unacceptable. The speed was sitting right there. The tunnel wouldn't let them use it. The man leading the project, Eiji Nakatsu, had an unusual second life. He was a birdwatcher, a member of the Wild Bird Society of Japan. And one of his young engineers said something offhand that stuck. When the test train shot into a tunnel, it felt as if the train shrank. Nakatsu turned that over. A body slamming from open space into a wall of resistance. He had seen that before, not on a railway, but at the edge of the water. A kingfisher hunts by dropping out of the air into a river. Air, then water, a medium 800 times denser, in a fraction of a second. By riches, it should land like a belly flop. It doesn't. It enters almost without a splash, because its long, tapered beak parts the water gradually instead of slapping it. So the team fired model noses of many shapes into a pipe and ran them through a supercomputer built for space research. The shape the math kept settling on, the one that made the smallest wave, was almost exactly the kingfisher's beak. Sit with what that means. A team of engineers armed with a supercomputer, searching for the single best shape to move between two densities, landed on an answer a bird was already born with. The kingfisher's beak isn't a metaphor here. It is a solution to the same physics, computed by evolution across tens of millions of years and written into the animal's body. Nakatsu didn't borrow a pretty idea. He read an answer. There is something humbling and a little embarrassing in that. Our finest machine, chasing a shape a fish-eating bird had finished perfecting before our species existed. And when they finally built the nose that way, the results read almost like a typo. By Nakatsu's own account, the redesigned 500 series cut the pressure wave by about 30%, drew roughly 15% less electricity, and ran about 10% faster than the train before it. One shape, quieter, cheaper, and faster, all at once. So how do you beat a problem that grows with every kilometer of speed? You stop fighting the air, and you learn to part it. The train that once fired a thunderclap out of every tunnel now enters it the way a kingfisher enters a river. The same air, the same speed, and barely a splash.